All right, assignment 12, 2.4 continued, graphing with Boolean variables. Our essential question is, how do you graph piecewise functions using Boolean variables? So the Boolean variables are that domain piece of the piecewise function. It tells you where your pieces start and stop, okay? And how can you find a value of a constant that will make a piecewise function continuous? All right, so those are our two essential questions. We are going to start with an exploration. So I gave you guys this exploration in class, and this is what we're going to work with. Okay, so we have our piecewise function here. K is some constant. We're going to plot the graph of f when k equals 1. Okay, so we're going to sketch that result. Now, hopefully you can do this without your calculator. I'm hoping that this would be pretty simple. And I'm looking at my domain here. I know that this piece is going to be when x is less than 2, and this piece is going to be when x is greater than or equal to 2. So the two graphs break apart, or the two pieces break apart at x equals 2. So I'm going to put 2 on here for sure. And this is probably going to need to go a little bit further. I know this needs to go a little bit further because I'm looking at this right here and I'm saying, hey, that's an x squared graph that's been moved to the right 5 units. All right, so starting with my first piece, x does not equal 2, so there should not be a solid dot on this graph at x equals 2. But this is just a linear function, y equals x plus 1, where my y-intercept is 1, and my slope is 1. So I'm going to go up 1 over 1. And then I can even go up one more, it's 3 here. If I go up one more and over one more, that's going to put me at x equals 2, so I need to have an open circle. Something like that. And then the other piece, now they're saying when k equals 1, so that way it'll be easy for us to graph. So the coefficient here, or the constant coefficient, is 1. Okay, so this is going to move over 5 spaces, so I know my vertex of the parabola is going to be here. It would be really helpful if I knew what the value was when x equals 2, right, because x does equal 2. So I plug 2 in there and I get negative 3 squared. Oh, great, that's 9. I wasn't quite prepared for that. So we're going to need to go a little higher. Okay, so at 2, when I plug 2 in, I get 9, and x equals 2 here. So I plug 2 in, I get 9. I know it's a parabola, so it's going to be, my axis of symmetry is here at x equals 5. So if I go 3 spaces to the right, right, because it's 1, 2, 3 spaces to the left, so 1, 2, 3 spaces to the right, I'm also going to be up at 9. So it's going to look something like this. You can plot more points if you want. And it's going to continue on after that. So obviously, function f is discontinuous at x equals 2. And tell what it means for it to be discontinuous at a point. Discontinuous at a point. So that takes us back to that definition of continuity at a point. Okay. So back to our last notes in 2.4, we knew that a function was continuous at a point if these 3 things were met. So if I plugged in that x value and I actually got something out, if my limit existed because both the left and right limits were equal, and if my limit as I actually approached that x value was equal to what f of c was defined as. So those are the three things that need to be true in order for it to be continuous at a point. So tell what it means for a function to be discontinuous. We can say a function is discontinuous when 1, f of c does not exist or is undefined. 2, the limit as x goes to c of f of x does not exist. And that would happen because the limit as x goes to c from the left of f of x does not equal the limit as x goes to c from the right of f of x. Hopefully you know this. This was on your test, chapter 1. Okay, and then 3, basically the other part would be that the limit of this does not equal what the actual value at c is, the actual output value at c. So the limit as x goes to c of f of x is not equal to what f of c actually equals. Okay. All right, next we're going to actually find the limit of as x goes to 2 from the left and the limit as x goes to 2 from the right. Okay, and the second limit will be in terms of k, because remember, in our original problem, there is a k being multiplied to the second piece, okay? So the first piece is when x is less than 2, so it's everything to the left of 2, right? So this means that I am approaching 2 from the left. Okay, so I'm going to use that first piece. And then for the second piece, the limit as x approaches 2 from the right, well, that's this piece, right? Because I'm coming to 2 from the right. What's my output going to be? All right, so then I'll use proper notation. So the limit as x approaches 2 from the left of f of x is basically going to equal the limit as x approaches 2 from the left of that first piece, x plus 1. Okay, and if I plug 2 in, do I get something out? I do. Nothing's undefined there, so I can just plug it in. It's really just going to be 2 plus 1, which is going to equal 3. Okay, and then the second part from the right, the limit as x approaches 2 from the right of f of x is basically going to equal the limit as x approaches 2 from the right of that second piece, which is k times x minus 5 squared. Okay, and when I plug everything in, I still have a k, and then I have 2 minus 5 squared, which gave us 9, right? So this piece equals 9k. Okay, so that's the first part. What must be true of these two limits for f to be continuous at x equals 2? What must be true for it to be continuous at x equals 2? So which piece of this is important for both the left and the right limits? Well, they must be equal, right, in order for them to be continuous. If we want them to be discontinuous, then they wouldn't be equal. So they have to be equal. They must be equal. Okay, so this piece here and this piece here need to equal each other at x equals 2 in order for it to be continuous at x equals 2. Right now, they're not continuous. I hope you all agree with that, right? There is a step discontinuity right here. So we are now going to find the value of k that makes f continuous at x equals 2. All right, wonderful. So we just said that those two need to be equal at x equals 2, right? So what we're going to do is we're going to set them equal to each other. 3 will equal 9k. And so now I'll divide both sides by 9 to figure out what k actually needs to equal. So k is going to equal 1/3. So I have a new piecewise function that I've just created. It is this. F of x equals the first piece, nothing's changed. And then the second piece, the k has changed, right? We now have a k. And then they want us to graph it. So what is this now going to look like? All right, so maybe I should have written it here so that we had it. I'm going to write it one more time, sorry. All right, so nothing's changed on that first piece. So when I graph that first piece, I should probably go a little bit further to the right. When I graphed that first piece, my y-intercept was 1. Use my slope to get another point. X equals 1. And then to get my next point at x equals 2, we use my slope one more time, but remember, it's an open dot, right? So this piece looks a lot like this. Okay, I still have the same function, I just have this coefficient, which is going to basically change this graph a little bit. So I'm going to go still graph it. I think my vertex will still be at the exact same spot. But now when I plug 2 in, let's see what this gives me. So 1/3 times 2 minus 5 squared. So that's still going to be 9. So I'm going to have 1/3 of 9. So that's going to give me 3. So at 2, my output is 3. And this piece, I can actually say, well, x can equal 2. So it looks like I need to fill in this hole. Okay, I know it's going to go down to 5. And it's also going to go over here. That's my axis of symmetry. So if I go over to 8, I should also have an output of 3. So that 1/3 coefficient here kind of makes this whole graph become fatter and shorter, right? Which will look something like this. Okay. So I'm going to write a note that my graph is on back. The graph in problem 4 has a cusp at x equals 2. What is the origin of the word cusp, and why is it appropriate to use in this context? This was in your book. The word cusp comes from the Latin word cuspis, meaning a pointed end. Okay, so cusp comes from the Latin word cuspis, meaning a pointed end. So why is it appropriate? Why is it appropriate for this new graph that we've just created? Well, what is this thing? It's a pointed end, right? Our graph has a pointed end, so it does have a cusp. So it's appropriate because the graph comes to a pointed end at x equals 2. Okay. Number 6, so suppose someone asks, is f of x increasing or decreasing at x equals 2? With k as in problem 4. So with the k that we have, the 1/3 that we got right here. How would you have to answer the question? What then can you conclude about the derivative of a function at a point where the graph has a cusp? So what's happening at this cusp? At x equals 2, is our graph increasing or decreasing? Hopefully you said neither. Right? It's not increasing or decreasing. So we can say at x equals 2, f of x is neither increasing or decreasing. So that means we have no rate of change there, right? So what can we conclude about the derivative of a function at a point where the graph has a cusp? If there's no rate of change, does the derivative even exist? So, and I think I've gone over this before in a previous video, but thinking about your rate of change here, well, as I'm coming from the left, I've got a positive rate of change, right? As I'm coming from the right, I've got a negative rate of change. So there is no one number that the derivative would approach. Right? So I can sit here all day long and estimate the rate of change from the left, and I can estimate the rate of change from the right, but it's not going to approach a limit for this rate of change. They're going to be approaching a positive rate of change and a negative rate of change. So there is no derivative. The derivative would not exist since it would have a positive rate of change from the left and a negative rate of change from the right. We'll just leave it at that. Okay, what did you learn as a result of doing this exploration that you did not know before? Hopefully you can figure something out to put there. So let's go back now and let me show you how to graph this in your calculator using Boolean variables. Okay, so that's what we're going to work on right now. All right, let's see, we got bright lights everywhere. What can I do here? How about that? That looks better. All right, so I'm going to graph two pieces of this function. One of them is going to be x plus 1, and the other one's going to be, for right now, k was 1, so we'll just do x minus 5 squared. I don't need that. Now here's the thing. You can make it restrict so that you're only graphing this piece up to 2. Okay, and then you're only graphing this piece beginning at 2 and moving forward. Okay, and the way that you do that is you basically divide out the domain. So you're going to divide this by, and put it in parentheses please, x, and now we need to do less than. So you want the inequality, the less than sign, and that is under, if you hit second and math. So under second and math, that's where your less than, greater than, all those signs are. Just select it, put it in there, less than 2. Okay, and then I'm going to do the same thing for my second piece. I'm going to divide it, this time by x. Now again, to find your inequality sign, it's second math. And we're going to do this one greater than or equal to 2. I'm going to check my window before I graph this. I think I'm going to make my x max larger. How about 10? And let me make my x max smaller. Let's go negative 10. And my y min is also going to be negative 10. Look at how cool that is. Is that not awesome? All right, and then you could do the exact same thing now for once we've made it continuous, right? You basically just divide out these Boolean variables, so these domains, okay? You just divide by it, okay? That's all under second math to get your inequality signs.